So our next speaker is Joel Tropp, who will be speaking about finding structure with randomness.
All right. I would also like to thank the speakers for the invitation. I lived in Durham for 8 years, and so it's always a pleasure to come back. So the work I'll be describing today is joint with Gunnar Martinson, who was my office mate in graduate school and is with the Applied Math Department at Boulder. And this research has been supported by a lot of agencies, in particular ONR and DARPA. Okay, so I like to begin this presentation with a notorious list of the top 10 scientific algorithms of the second half of the 20th century that appeared in a special issue of Computing in Science and Engineering. So there are a lot of things up here that I think are incontrovertible examples of fundamental algorithms. Fast Fourier transform, simplex method. But one thing that always struck me as very strange is this item that I've highlighted here, the decompositional approach to matrix computations, which doesn't sound much like an algorithm to me. So I opened up this issue to the article by Pete Stewart, where he describes why it is that this item is on this list of algorithms. And he writes, "It is not our business as a matrix algorithmicist to solve problems. It's our business to build platforms from which people can solve problems." So what he means by this is that matrix decompositions are a little like Swiss Army knives. Once you've got one, you can do a lot of different tasks. So for example, if you have an LU decomposition of a matrix, you can solve a linear system with not one right-hand side, but as many right-hand sides as you want at a very low marginal cost. You can even use it to compute determinants and other things like that. So these decompositions are really useful for a lot of different applications. And the other point that I would like to emphasize here is this item at the bottom, that the decompositional approach to matrix computations has led to highly efficient black box software for performing these decompositions. So the advantage of this point of view is something that you experience every day when you use MATLAB. You want to solve a linear system, you don't have to worry about the details. You just type LU, you get an LU decomposition, you can do with it as you please. And I don't think it's an overstatement to say that this point of view has revolutionized the way that we perform linear algebra computations throughout science and engineering. This has really made a large part of signal processing, data analysis, statistics, and numerical PD possible. What I'm going to argue today is that it is now time to open up these black boxes and have another look about what's inside. So the reason for that is a little bit subtle. So you might say, well, what's wrong with all these classical methods? MATLAB works great. And the answer is that there's nothing wrong. These methods are awesome. But they don't do so well in some circumstances that we start to see more often now. When the matrices are relatively large scale, these algorithms may not be very effective. And they don't always work as well as we might like on modern computational architectures. And the reason is that even though we tell our students when we teach algorithms that, especially numerical algorithms, that the number of floating point operations is really a fundamental, or maybe the fundamental measure of the cost of the algorithm, it's not really true in a lot of cases anymore. Jim Demmel has really spent a lot of time and effort making the argument that we now need to worry more about the communication costs. We worry about how long it takes to transfer data to the processor. We worry about how long it takes to move data around on the network. And that these costs actually dominate the cost of the floating point arithmetic in a lot of classical algorithms. So we need to fix this problem. So one approach to doing that is to design algorithms that are multiplication rich. And the reason is that matrix multiplication is probably the thing that we're the best at. Modern platforms are optimized to tear through these things faster than almost anything else. You can do this in all sorts of architectures. You can chop it up however you like. this is something that we do well. So I'm going to talk about a technique that in some ways is not that new, but has certainly become a lot more timely now, and a new analysis to support it that justifies building algorithms for computing matrix decompositions out of matrix multiplies and some other lower order operations. So I'm going to give you a description of how you might use this approach to compute the truncated SVD of a matrix, and then I'll go into the details about the randomized part of the algorithm. So let me remind you that a truncated SVD takes some big matrix A, which is m by n, and expresses it as a matrix U with orthonormal columns, a diagonal matrix sigma with non-negative entries, and a matrix V star whose rows are orthonormal. And you'll note here that the only way we can accomplish this is if we found some structure in the matrix A, because on the left-hand side there are a lot more degrees of freedom than on the right-hand side, because m times n is a lot bigger than m plus n times k. So if we want this approximation to be good, the only way we can achieve this is if we found some structure in the matrix. Okay. I don't need to persuade you that this is an important problem, so I'll leave it at that. So there's a two-stage approach that we've proposed to solving these problems. The first stage is to find the range of the matrix, and the second stage is to use the range of the matrix to construct the decomposition. So let me say a little bit more about this. So the idea here is that we're going to go looking for a subspace with k dimensions that somehow captures most of the action in the matrix A. So I'll show you a picture to try to emphasize what's happening in a minute, but the goal here is really just to find a subspace where A is doing most of its dirty work, and we'll ignore the part of the codomain where the action of A is nominal. And the way we'll quantify this is by looking for a matrix Q that has orthonormal columns, so that if we project A onto the range of Q, then we've got most of A, and that there's very little left over. And we'll do this with a randomized algorithm. As you'll see, this will really involve one matrix multiply and some auxiliary work. Now, what may not be obvious, and that I'm not going to have time to present in detail, is the fact that once you have this subspace, constructing the decomposition is pretty easy. So what we'll do heuristically is we'll use this subspace Q to reduce the size of the problem. So we'll multiply Q back into A, we'll get a much smaller matrix, and then we'll apply a classical SVD algorithm to this small matrix. So as I said, classical SVD is awesome if the matrices aren't too big, and so this step's sufficient. And when we're done, we'll have the truncated SVD in factored form. So you can use this approach for a lot of other kinds of matrix decompositions. The key idea here is we'll use a randomized algorithm to go looking for the range of the matrix, a subspace that captures the action of the matrix, and then we'll use the subspace to build a decomposition. So the total cost for computing an SVD in this fashion are as follows. Using this two-stage approach, you need two matrix multiplies and an auxiliary amount of work that's linear in the ambient dimensions of the matrix and quadratic in the target rank. Meanwhile, if you're using a classical sparse method, like a Krylov subspace technique, you need k matrix vector multiplies for the classical techniques. And so you see the amount of arithmetic's about the same as with the two-stage approach, but it's organized in a much less efficient manner because you have to do these multiplies sequentially. And then you need a little bit of auxiliary work. In contrast, dense methods are not based on multiplies. You have to go digging around in the matrix looking for columns that have particular properties. It doesn't take any more arithmetic, but because of the way it's organized, these things are extremely inefficient for large data and on modern architectures. So because if you believe that matrix multiplies are really the tool in your toolbox that is the most efficient, then these two-stage randomized algorithms are really extremely effective ways to accomplish these decompositions. And you can use the same pattern to develop algorithms for QR, for Koleski, for column subset selection, a lot of other tasks. And this is all discussed in the survey paper that I'm presenting. So let me pause and ask if there are any questions about this overview of the algorithm before I continue with the description of the randomized rangefinder. Well, the rank of A, I mean, is arbitrary. K is sort of the target rank. You would believe that, at least in principle or heuristically, you believe that A is well approximated by a rank K matrix. In practice, use an adaptive algorithm to decide when you've got a good enough approximation. I'm not going to say too much about that. Yeah, you think about K as the numerical rank, but the way I present the algorithm, it's a parameter. In practice, you determine it adaptively. Other questions? Always more questions after the coffee break. Yeah. You quantify it in terms of a spectral norm error. I'll show you later. Okay. So most of the interest in these approaches really is in the randomized technique for finding the range of a matrix. So I'm going to spend the rest of the talk describing this approach and the error estimates we've obtained, which are really somewhat different from classical Krylov type methods and really provide a new justification for why these algorithms are effective and why they should not be considered as iterative techniques. Okay, so here's the basic idea. So for now, let's assume that we've got a matrix A that is actually rank deficient. So its range is an honest-to-God k-dimensional subspace of the codomain. Now, we're going to go looking for this k-dimensional flat in this big ambient space. And so here's one way you might try to do that. You're going to reach up in the sky, you're going to pull out a random vector omega 1, you'll multiply that into A, you'll get a vector A omega 1, and that's evidently in the range of the matrix A. Okay, that's good. We found one direction. Let's try again. We reach up in the sky, we pull out a random vector omega 2, we multiply into A, we get A omega 2, which is also in the range of A. And you can see that it's pointed in a somewhat different direction. It's random after all. So we found another direction in the range of A. Okay, we're making good progress. Let's do that k times until we've multiplied in k vectors. Now, because random vectors are highly likely to be in general position, this collection of vectors A omega 1 through A omega k are still, well, they're k vectors in general position in a k-dimensional space, so they're linearly independent. And so if we want a basis for that k-dimensional flat, we just orthogonalize them. Okay. Now, I will point out that you have to be a little bit careful orthogonalizing these vectors because they tend to be oriented along the major axes of this ellipsoid you get if you multiply in the L2 unit ball into the matrix. And so the vectors here do tend to point similar directions. So if you're not careful with the numerical aspect of the orthogonalization, you will get garbage. So it's important to do this the way that your linear algebra professor taught you. Numerical linear algebra professor. Okay. Now what happens if A is not in fact rank deficient, as most matrices we encounter in the universe? So let's imagine now that in fact it's got some action in the directions orthogonal to the overhead. So it actually jitters vectors out of this k-dimensional space. Well, when we start multiplying vectors in, they're still reasonably well aligned with this k-flat, but there's some extra components. And it turns out that we'll need a few extra vectors to really make sure that our samples, A omega 1 and so forth, are actually well aligned with this flat so that they really do cover this space. And so it turns out that taking a few extra samples from the range of A is extremely important for these algorithms to work effectively in practice. Okay, so let me convert this into an algorithm. So our input is an m by n matrix A, and we're going to take L samples from its range. We'll do that by drawing an m by L random matrix omega. We'll multiply that into A, As I mentioned, we're really good at matrix-matrix multiply, so we're happy about that. And then after we're done, we're going to orthogonalize the columns of Q, of Y to get this matrix Q. Okay, so the cost is 1 multiply and an auxiliary amount of work that's only linear in the ambient dimension of the big matrix. Okay. So there is a lot of background literature on this that I am going to pass over right now. We've got about 10 pages of discussion of related work in the paper, so if you'd like to know where these ideas come from, I encourage you to have a look at that. Now, there are a lot of implementation issues that you do need to pay attention to here. The one that I often get asked is, how do we decide what L is? In practice, you actually use a randomized error estimator to decide when you've approximated the input matrix well enough. So you can basically do this for free without any extra computation. So you, roughly speaking, you build the spaces, say 32 columns at a time, and when you've decided that you've got a good enough approximation to the range of A, you stop. How does L compare with the target rank? So if we believe that this were a 12-dimensional range, we'd like a truncated SVD with k dimensions, how do we pick L? It turns out that usually 5 or 10 extra samples is entirely adequate. I'll justify that in a minute with an error bound. You can use a lot of different kinds of random matrices. I'm going to focus on Gaussians here because they provide the best error estimates, but it may make sense to use a structured random transform for some applications. And the final 2 implementation details are that you really do need to be smart about the matrix-matrix multiply if you want the algorithm to be efficient. And if you are not careful with your orthogonalization, you will get garbage. So you do need to be careful about how you implement this approach. So let me pause and ask if there are questions about the algorithm, the intuition, or the implementation. Yeah, Martin.
Suppose we want to thumb our nose at a numerical linear algebra professor and be less careful with the calculation. Would it suffice to make L a little bit bigger?
No. What happens is that after you start orthogonalizing vectors, you start getting round-off errors, and that's all that's left. So you either need to do this using householder reflectors or something stable, or you need to use what's called double Gram-Schmidt, which Gram-Schmidts all the vectors twice, and somehow that works, which is a mysterious but true fact. Did you have a question? Okay. More questions? Gaussian works awesome. Random signs works a little less well. Things like structured random transforms often work well, but not always. It's a complicated issue. There's some people who have developed software for this and implements somewhat complicated random transforms that have some balance between the cost of drawing the random numbers in the matrix and the stability of the random matrix in practice. The nice thing, by the way, about Gaussians is that you can draw the entries independently without reference to each other, so you can do this in a distributed fashion if you need. That's, for example, why you don't use hard distributed matrix on the Stiefel manifold. You don't want to orthogonalize the columns if you can help it. Amit?
The columns of the matrix are not equally drawn. Does it make sense to...
Of which matrix? No, not for. If you use a Gaussian, it doesn't care.
Even if I have one column to be on time?
Gaussian just doesn't notice because it's uniformly distributed, so it's perfectly happy. On the other hand, if you're doing something like sampling columns, you need to be much more careful. Okay, let me move along and show you some numerical examples because there's really no point in talking about this if these algorithms don't actually work, and they do in fact work. So here's an example from numerical PD, which my co-author developed. So what we're doing here is we're taking a Helmholtz integral operator and discretizing it on, so it results in a 400 by 400 matrix. So it's pretty small. And because of the physics, it's got about 100 singular values that are substantial, and then after that, the singular values drop off exponentially. So What we've got here on the bottom axis is the total number of samples we've taken, or the total rank of the approximation of the matrix we're making. On the vertical axis, we have the error. So the red curve here is the optimal approximation error that you get if you just compute a truncated SVD with rank L. The yellow curve is what happens if you run this algorithm with L samples. So you see that you pay a very, very small price for using this randomized approach. So you do nearly as well as the optimal using L samples. So this is really comparing the L truncated SVD with the approximation you get using an L-dimensional subspace. The blue curve is the randomized error estimator, which tells you when to stop. So you see that when the error estimator says you've hit an error of 10 to the minus 8, you really do have an error of 10 to the minus 8, and you can quit with some confidence that you've approximated the matrix well. Yeah, sure enough. Sorry, I'm colorblind. So, any other questions on this chart that I can answer? Okay. So here's an error bound to justify that these algorithms actually work. So this is the simple version for talks. Turns out there's a lot more packed in here that I'm leaving out. So we'll assume that the matrix is m by n, and for simplicity we'll assume it's tall. Doesn't really matter. We'll assume the target rank is k, and that the optimal error is the k plus first singular value of a. We'll draw a test matrix, which is standard Gaussian and has k plus p columns. So k plus p is the number L that I mentioned before. Then if we use this randomized rangefinder algorithm, it turns out that the error that we compute is proportional to the optimal error. So it's got one copy of this k plus first singular value, and some additional copies, some small polynomial factor depending on the parameters. So let's have a look at this. So you see that the error increases slightly as we increase the target rank. You will see this effect in practice. It's real. And as you start increasing the oversampling, p, the error starts to decline. So when p is equal to 0 or 1, the result is vacuous. But by the time p equals 2, you're in business. You only need 2 extra samples before this error bound is in force. By the time you take p equals 5, you've already killed off the leading constant. And if you take p on the order of k, this leading term here is about 1 over the square root of k. So if you oversample by a factor of 2, you're already seeing some improvement in the leading term of the error. Now, this term square root n is actually the L2 norm of the residual singular values of a, the ones that you've missed. And so if the tail singular values of a drop off, you don't see the dimensional factor, but you might in the worst case. So some people worry that this is an error in expectation rather than an error in probability, but there are some measure concentration effects here. They're relatively weak, but nevertheless they're strong enough that the error really is not much bigger than this in practice. My student did some experiments and reported that the error bound is typically within about 30% of the actual error that you obtain when you run the algorithm. So this really is actually a very accurate description of what this algorithm is doing in practice. So are there any questions on this theorem? Yes.
Do classical methods also get this sigma k plus 1, or do they also have some?
Well, the classical methods do things a bit differently. I mean, they don't tend to aim for, they're asking for something different. They're not doing matrix approximation, they're looking for invariant subspaces, and so their behavior all depends on spectral gaps and other things. They ultimately would obtain the optimal error sigma k plus 1. This is, the comparison's a little bit complicated because you're using the subspace to go build the SVD afterward. And the classical SVD algorithms would get the error down to sigma k plus 1 without really any extra factor. We'll address this in just a second. Any other questions on this? Okay. So it turns out that in practice, you need to be a little more careful than this because a lot of the matrices you care about have singular values that decay fairly slowly, and so the square root n term may not actually be the square root of n, but it's maybe not so small because the residual singular vector values don't decay that fast. So at least nominally, the approach that we'll pursue to solve this problem is to apply the same algorithm to a power of the matrix A. So if you look at the matrix A star to the Q times A, this matrix has the same left and right singular vectors as A, but the singular values are exponentiated to the 2q plus 1 power. So if the spectrum of A decays a little bit, the spectrum of A to the 2q plus 1 decays a lot. And as a result, this new matrix really will exhibit some spectral decay almost all the time. So you need to be careful when you apply the algorithm in this fashion. I'm leaving out all the details, but the only difference nominally is that you need a few extra multiplies and a little bit of extra arithmetic. But you do need to be careful forming the matrix vector product and doing the orthogonalization. And so if you do this, in the eigenfaces example, so we've got a 5 gigabyte matrix, which, I mean, let's be honest, is really only a medium-sized matrix. But nevertheless, MATLAB does not like computing its SVD. If you go looking for the left eigenvectors of this singular vectors of this matrix, it takes some effort. So let me show you what happens when you use this power scheme to accomplish that. So this chart's a little bit hard to read, so let me walk you through it. So the first picture is a plot of the approximation error using L samples for different exponents Q in this power method. Okay. You see that raising Q improves the error so that it's essentially optimal. The red curve is the optimal value. And in the right picture, we've got the rank of the, we've got the estimated singular values of the matrix that we get if we actually compute the SVD. And by taking Q to be 2 or 3, we effectively get the optimal values for the singular values of the matrix. So this algorithm is extremely effective with Q equals just 2 or 3. Okay, there's an error bound, but if you're interested in learning more about this, we have a survey paper that just appeared in SciAm Review in June and contains an excruciating amount of detail about all of these topics. Thank you for your attention.
Since we're up against the break and we're a little late, maybe just one additional question? No? Let's thank him again.
Thanks.